Welcome back, everybody. This is our video solution to problem 3 from Quiz 2, Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. In this problem, we're given a vector space V over a field F in which 1 plus 1 does not equal 0. All right, that's kind of a strange looking condition, but this is going to rule out what are called fields of characteristic 2. And we're going to assume that a list UW spans the vector space V. And we want to prove then that the modified list U plus W, comma U minus W, also spans V. So let's briefly recall what that means, right? If I want to show that V equals the span of U plus W, U minus W, what is that span? So the span of U plus W, U minus W is going to be all expressions of the form alpha times U plus W plus beta times U minus W, where here alpha and beta are in the field. So these are linear combinations of the vectors U plus W and U minus W. Now, I already know that V is equal to the span of U and W. Okay, so that must be useful somehow. Well, in principle, if I want to show that this span in the top line is equal to V, I would have to show that every single element of V is expressible as a linear combination of U plus W and U minus W. And that feels like a lot of work. I don't want to do it. So instead, what I'm going to do is utilize a result that we proved on the homework. So let's write this theorem down. And it says that if I have a list L prime, and it's contained in the span of another list L. All right, so I check every element in the list L prime, and look at that, it's in the span of L. Then the entire span of L prime is contained in the span of L. So in our case, what I would like to do is to show that U comma W is contained in the span of U plus W and U minus W. Because if I can, then that's going to imply that the span of UW is contained in the span of U plus W, U minus W. But we already know that the span of UW is equal to V. And of course, the span of anything is going to be contained in V. And so this would then imply that V is equal to all the stuff in the middle. So V in particular would equal the span of U plus W and U minus W. All right, so this is what we want to do. This step right here is all we need. We need to show that U and W both can be written as linear combinations of U plus W and U minus W. Well, how do we do that? Well, nice thing is we could just start writing this in a slightly different way. What if I have U plus W and then I write U minus W? And man, that just looks like something I want to do something to, like add maybe, right? So what if I add these together? If I add these together, I get U plus U, which is 2U, and W minus W, which is 0. And this is exactly the point where we needed this weird extra hypothesis. We're assuming that 1 plus 1 does not equal 0. If I, on the side here, write U plus U, this is the same thing as 1 times U plus 1 times U, which is equal to 1 plus 1 times U, which is equal to 2 times U. Now, if 1 plus 1, and that's what 2 is supposed to be, right? If 1 plus 1 was equal to 0, then I would get 0 times U, right? I could actually, get 0 times U here. Right? That would be really weird. 0 times U, which is equal to 0. And that wouldn't help me very much, right? That actually is not what I want to get here. I'm trying to actually, at the end of the day, get some non-zero multiple of U. So that would be really bad. But we get to assume that that doesn't happen. So 2, which is 1 plus 1, is not 0. And that means it's going to have an inverse. Okay, so here I was able to get 2U. But 2 inverse is an element of F because 2 is not 0. And so this means that I'm actually going to be able to write U How? Well, I'm going to take 2u and multiply it by 2 inverse. Okay, but 2u is what I got when I add these vectors together. So this is u plus w plus u minus w. If I distribute this 2 inverse, then I get 2 inverse times u plus w plus 2 inverse times u minus w. And so what I've just shown you is that u can be written as a linear combination of u plus w and u minus w. And so this is in the span of u plus w, u minus w. Okay, well now we just need to get w in the span as well. And the way we do that is almost identical. Instead of adding these together, I'm going to subtract them. When I subtract them, u minus u will be 0, w minus negative w will be 2w. So I'm just going to get here almost the same thing. 2 inverse by u plus w, but now minus 2 inverse by u minus w, which is again in the span of u plus w, u minus w. And there we go. We've shown that both u and w are in the span. That implies that the span of uw is in the span, but that means that v is going to have to equal that span. And there we go. All right, we will see you next time as we move on to linear independence. Bye-bye now.